RGR, relative growth rate, we are looking at a rate that is equal to the ratio between, we're looking at a constant that is equal to the ratio between the rate of change or instantaneous rate of change of the derivative y prime over y. And this is essentially a differential equation, and its growth if this constant is positive. So you have constant ratio of rate over the function, and it turns out that this y will be in this case an exponential function, and it's a growth function if k is positive, and likewise RDR, the relative decay rate, will be the same expression y prime over y, with the exception that the rate of change y prime is negative, therefore the ratio between the rate of change and the function is negative, I should say. Therefore we have decay. And the theorem states that the unique solution to this differential equation k equals y prime over y is given by the following exponential function, or natural growth function. Some people call it, give it that name. Y of t equal y sub 0, which is the initial value of the function, times e raised to the power of kt. This function is enormously important. It's a component in the solution to most differential equations. Okay, so here's the first example for the day. Let's call it example 1. Okay, the half-life of radium-226 is 1,950 years. Radium-2006, one of the elements discovered by Marie Curie, the French/Polish physicist. Another element, a radioactive element, she named it polonium in honor of her native country, but her work was done mostly or almost exclusively in France. And actually she married a French physicist that also contributed to this science, but is somewhat less known than Marie Curie, or Marie Curie. All right, so we have this half-life. In other words, for any given quantity, after 1,950 years, we'll have half the quantity of radium-226, that particular isotope of the radium. And of course, this can be useful in estimating the age of a substance, but most commonly we use carbon-14, C14, for that purpose. Here are some questions associated with this. Find a function m, the mass, as a function of time, if m sub 0, the initial mass, is 100 milligram. Okay. B, what will be the mass after 1,000 years? Okay. Well, we know off the bat that it will be more than 1/2, because it takes almost 2,000 years to reduce the initial quantity to 1/2. And part C, find the time t such that m of t, the mass, is 30 milligrams. Okay. So what happened with radium is as well as other radioactive substances, is there is a constant emission. There is a constant emission, and the rate of change is proportional to the mass. And remember, the way we defined relative growth rate or relative decay rate, we were looking at K, a constant, where the rate of change, y prime, in this case will be dm dt or m prime, to the mass m of t remain constant. And we know that the solution will lead to something like this, to an exponential decay function of this sort. Let me take you to, well, no, I'm not going to use previously obtained knowledge. Let's say the following. For part A, half-life is the time where t such that m of t equals 1/2 of the initial m sub 0. Okay? So, actually I had room to write it here. So, what is m of t? Well, if we assume that this behave exponentially, then m of t, I'm looking at the solution to differential equation, is m sub 0 e to the kt, and therefore we substitute m of t with 1/2 m sub 0, and we have 1/2 m sub 0 equal to m sub 0 e to the kt. Okay? And of course, m sub 0 and m sub 0, we can divide both sides by m sub 0, the initial quantity, and at this point we can apply the natural log, and we're going to say that natural log of 1/2 equal kt, natural log of e, and of course natural log of e is 1. And from here we can extract two things. We can extract a formula for half-life, and I'll call it T sub h. H stands for the half-life, and we're going to say that T sub h, the half-life, will be the natural log of 1/2 divided by k. You may remember that from pre-calculus or college algebra, the half-life formula. I want to tweak with it a little bit, okay? If you consider what is 1/2, and you can write 1/2 as 2 to the negative 1, right? 1 over 2. So the half-life will be the natural log of 2 to the negative 1 over k, and this in turn will be, by the property of logarithm, negative natural log of 2 to the k. Okay? Natural log of 2 is 0.691, sorry, 0.693148. So, or 70% of, but this is an important expression right there, that it's easier to remember than value for natural log of 2 than the value for natural log of 1/2. And also natural log of 2, if you remove the negative sign, do you know what you get? The double time. The double time. Okay? Might as well, let's write it in the next page. Go ahead, Jason.
So, I'll take the next one. So why is the 2 to the negative 1 not equal to 1 over 2?
2 to the negative 1 is 1/2, which is what we have here. And I want to express this result in terms of natural log of 2, because the quantity natural log of 2 is very common. It's nearly 70%, or 0.69. To be precise, or more precise, 0.693. Okay? So instead of expressing my half-life in terms of natural log of 1/2, let me write something on the next page, and you'll see why I chose to write it like so. Okay. On the next page, let's recall the following. You have the half-life formula, which I just introduced. And the half-life formula we're going to say that T sub h equals negative natural log of 2 over k. Remember, k is negative because we are talking about decay. So you can see that the time will be positive. You have negative divided by negative. On the other hand, what is the double time formula? If we change one thing in the previous page, if we change this statement right there, instead of m of t equals 1/2 m sub 0, we'll have m of t equals 2 times m sub 0. We're going to get the double time formula. And the result will be natural log of 2 over k. So we can write t sub d for double time will be just natural log of 2 over k. So look at how similar these two formulas are. So if you have negative, you know that you have half-life. If you have positive, you know that you have the double time. In any event, natural log of 2 is 0.693. So we are dealing with the same number. Okay? Was the question in the back over there? Eli? No? All right. So now we continue. In this case, the half-life, T sub h, is 1,950 years. So from here, we can extract the value of k, the decay rate. Okay? And the decay rate going to be, so k equals negative natural log of 2 over T sub h, or in our case, it would be negative natural log of 2 over 1,950. And you can either evaluate the value or keep it like that. I told you on Monday that you need to be very careful when you evaluate component of exponential growth and decay. Every time you use a decimal form of this number, natural log of 2 is a rational number. In other words, it has a non-terminated decimal part. So you need to round it one way or another. Whether you round it after 3 decimal places or 6 decimal places, you're going to introduce a rounding error. Now, if this is the exponent, a little rounding error in the constant may create a large rounding error after you raise it to the power, or you raise it to the exponent. So it's sometimes, if you want to increase accuracy, you want to keep this as, instead of writing a value on your calculator. So we need k. Going back to what we are required to do, we want to know what is the value, what is the time if, what is m of t if m sub 0 equals 100? Since now we have k, we can say that m as a function of the time equals m sub 0 e to the power of k, but instead of k, it would be natural log of 2 over 1,950 times t. And that would be a very good answer. Actually, that would be an excellent answer, because I kept everything precise rather than rounding. Okay? And now we are getting to part B. And part B, we asked to find what happened after 1,000 years. Well, that's easy enough. After 1,000 years, if we have we start with 100. By the way, this is 100. So you can go ahead and replace m sub 0 with 100. Well, no, that's actually, we are told in part A. So really, we should have 100 here. So you may want to put 100 right there. So it will be 100 times e to the negative natural log of 2 over 950 times 1,000. Okay? If I was a smarter person, I would put 1,000 over 1,950 and then multiply it by natural log of 2, like so. Now, at this point, I have no choice but put it in my calculator and get the result. And if I calculate it correctly, it ends up being 17.09 milligrams. Jason, I saw you operating your calculator. Do you concur with this result? Or anybody else? Oh, you were doing something here? That's fine. Anyway, I think this is something you can verify, so let's not dwell on this one.
Yeah, that's right.
Well, every now and then I get lucky and I get the right answer. But let's look at the last one. M of t equal 30 milligram, and we need to find the time, t, or how many years. So we're going to set up an equation. We're going to go back to our solution in part A, and we're going to set 30 equals 100 e to the kt, but we know that k is the natural log of 2 over 1,950 times t. And then the goal is to extract t out of this. And of course, we divide everything by 100, and we apply the natural log. Okay? So from here, I'm going to skip the division, and 30 divided by 100 is 0.3. So natural log of 0.3 equal, apply the natural log, and again, this is the exponent, so it will be negative natural log of 2 divided by 1,950 times t. Now, can you tell whether the natural log of 0.3 is positive or negative? Ignore, even without looking on the right-hand side.
What's going to be negative because of decimal?
It's going to be negative, I don't know about that, but when the natural log is 0? Natural log of what number is 0? 1. So the natural log will be positive if the argument is greater than 1. The natural log of 1.01 is positive. The natural log of 1 is 0, and the natural log of every number between 0 and 1 will be negative. Okay? And of course, natural log of 0 does not exist, nor the natural log of negative number. So the argument has to be positive. But for all the positive argument, greater than 0 but less than 1, the natural log is negative. So we have negative on the left. Natural log of 2, since 2 is greater than 1, natural log of 2 is positive. The time is positive, so negative equal negative. Now to solve this, of course, all we need to do is use a little extraction here, and we're going to say that t equals negative 1,950 times natural log of 0.3 divided by the natural log of 2. Can I simplify the ratio of the two natural logs? Do I have a logarithmic rule here? Folks, this is a trick question. There is no. If it was natural log of 0.3 divided by 2, then it would be the difference. It would be natural log of 0.3 minus natural log of 2. But there is no simplification of ratio of natural logs. So keep it at that. Okay? Calculate, and the result will be approximately, well, actually, it's pretty accurate result. 3,387 years. Okay? So before we depart ways from our exercise, let's see if the last two results make sense, consider the fact that we started with half-life of 1,950. Does it make sense? Well, think about the answer in part B. It takes 100 milligrams to reduce to half, or 50 milligrams, over a period of nearly 2,000 years, 1,950. So it stands to reason that after 1,000, it will be reduced only by nearly 30 milligrams. Oh, and we'll have more than one half. We'll have about 70 milligrams out of 100, or 70% of what we started with. On the other hand, when we reduce it to 30 milligrams, or 30% of what we started, we know that it will be more than 1,950 years. And indeed, this result makes sense. So both the results are in accordance to the common sense of the data we were given.